Let me start. Okay, welcome all of you. Good morning and good afternoon to the session 10. So today what we plan to do is I will maybe till the break we'll have some session on control hazards, and then I would like to go through the online simulation tool. I don't know how many of you have practiced it. We'll see that today because you are now ready to understand it. I have taught you all the things what is required. So let us now start with a quiz. Okay. Start the day with a quiz. I don't know how many of you are there. 33 people. Okay. So let me show you the MIPS pipeline now. Can you see a difference here? If you are alert, you should be able to see the difference here. 1 second. I'm not able to get the pen. One second. Okay. So let me come back. Here, if you have seen, if you are alert enough, you see that this zero flag check, it shows zero flag, but it need not be only zero flag. It can be any flags which are being tested in the ID stage. This is an ID stage. As I told you yesterday, the register set has the flags also, and any control instructions, especially the conditional instructions, if they need to check any flags, they can do it in ID stage and take a decision whether to jump to the branch to a particular location or continue with the sequential execution. So that decision is also taken here. So if you can see, both adding the offset with the PC plus 4 value which is available here and checking the flag is done here. Okay. So based on this, I don't want to explain anything more. I want you to answer my question here. Number of cycles wasted for a unconditional jump or for a conditional jump is the same in this pipeline. I am making a statement. The number of cycles wasted is the same in both the cases, which is just one cycle for both. I want you to tell me whether the statement is true or false. Okay. 1 second, something on chat. Okay. Just hold on. I got some answer. Let me launch the poll. So please enter your answer whether it is true or false. Only 22 people have responded out of 40 are there, around 39. If you can quickly answer, I can proceed further. Okay, let me stop it. Some people have decided not to answer, or okay. Okay, guys. So let me share the results. So majority got it right. So let me explain for those who have still given a wrong answer. See here what is happening. Understand the situation where a jump or a branch instruction is coming in. It could be conditional jump or unconditional jump. The difference in conditional and unconditional jump is this checks some flags also. If you notice in this pipeline, both the adder as well as the hardware to check the flag is in the same stage, which is ID stage. Now imagine an instruction which is a branch coming in. It will be passed on to the pipeline register. While it is being passed, the instruction PC plus 4 comes here. Now this stage knows that it is a branch or unconditional branch. It's a conditional branch or unconditional branch. Based on that, it may check the flag or it may not, but it will find out offset is given. So it will find out the relative address where the PC should be loaded with, and it is getting a PC plus 4 as an input. So it will perform the addition and it will get a target address. Target address will be loaded through this mux into the PC. So the whole thing happens, it's like a combinational circuit, and it can happen within a single cycle. As long as the data which is required is PC plus 4 is available, flags contents are available, and the offset value is available within this stage, with the help of this and this, it can actually find both. It can find the offset and then take the target address and then take a decision based on whether this flag condition is true or not. Then based on this input, either the value coming from here will be taken in, or it will be the same PC plus 4, which is so in this case it will not do the PC plus 4 because yeah, it's true, PC plus 4 only, because it has to continue with the same instruction. So it will take the PC plus 4 value and then push it in if the condition is not true, if it is a conditional statement. If it is an unconditional jump, it will default, it will push the new value which is being computed, so that control will flow there. Now during this situation, already there is one instruction which is fetched, which is PC plus 4 is already fetched. So the new address which is loaded into PC will be effective from the next cycle. That means this PC plus 4 will move into this stage and a new target address will be picked up by the IF stage. So there is still a wastage of one instruction which is PC plus 4. That instruction would be brought in and then it will be ignored. Okay. So that is what we learned yesterday. Now I'm happy that majority of you are getting it. So let me now proceed further. It's true. Okay. Now I only spoke about the branch instructions and what is it causing to the pipeline. It is causing some delay in the pipeline. It is causing some stall in the pipeline. So which is nothing but a control hazard. If you remember, data hazards cause some delay. If forwarding register is also not helpful, then it is causing some delay. Otherwise forwarding was put in to compensate for the problem that we faced with the data hazard forwarding logic. In the control hazard, we are making some progress by moving this into the ID stage so that the delay is minimized, so that we compute the new address as early as possible within the pipeline and even check the condition for the jump, whether it is going to happen or not. We are doing it ahead on the pipeline so that we are only wasting one instruction which has been fetched, thinking that instruction will flow through sequentially. Okay. So we are making every attempt to minimize the number of stalls introduced in the pipeline. In case of data hazard, we introduce forwarding logic so that the results are given to the ALU early so that it can proceed with the sequential instructions if it is dependent on the data which is coming from the instructions which have been executed earlier. So that was the solution for data hazard. And what is the solution for control hazard? It is adding this adder and adding it here, not here. We were doing it in flag checking. We were doing it here. We moved it here. So these are all some optimizations which have been done on the pipeline to effectively reduce the stalls in the pipeline. Okay. Stall means execution is stopped till some decision is taken. Okay. Now, what is control hazard? All of you must have understood by now. Let me explain it for the reading purpose. It arises from branch or jump. Different processors call them as jump or branch. It depends on the processor, but the logic is same. Don't think that it is only happens in branch and does not happen in jump. It is both are same. It's a in Intel processor we call it as jump, JMP. Okay, in Intel processor JMP is the instruction which is equivalent to jump, which is a unconditional jump. And in Intel, jump on carry was an instruction. It is equivalent to ARM BEQ, branch on equal. Both are similar instructions, and both are conditional instruction, jump instruction, but ARM calls it as branch equal to, whereas it is checking the zero flag, whereas jump on carry is checking the carry flag. Okay. Jump on zero is one instruction in Intel. So these are all different instructions. You can, if you read any of the other processors, you should be able to relate all these things irrespective of what is the processor you are reading about. Okay. It is all the same logic everywhere, except that each processor vendors like Intel or ARM call their assembly instructions in a different way to just differentiate themselves. So it is like a C program and other languages what we have seen. So assembly programs also have different notations and different ways of calling similar instructions. Okay. So it is control flow instruction. Control hazard can cause a greater performance loss. See, in data hazard, the hazard was causing a delay in the execution, but it was not causing the whole pipeline to be flushed. It was not making whole pipeline to be flushed. It was only delaying some execution, but it was continuing to go through. So data hazards, because of this, they cause less of a performance impact because of the data dependencies in the pipeline, whereas control hazards cause little more damage because they have to flush the pipeline. That means new instructions have to be fetched. Remember, when you have to jump to some other location, it is in some part of the memory. That memory address need not be in the cache. Which cache? Instruction cache. So in sometimes it may not be in the data main memory also. That code may not be that library function. If you're calling a printf and printf is not loaded, the library is not loaded into the main memory, you may not even have that piece of code in the main memory. So a control flow instruction can cause major impact to the performance. It could be even the process will be swapped out and then new process have to be brought in. By the time the library is loaded into the main memory and the code is available and it is moved to the cache when it is accessed. So there are more possible delays which are likely to happen when you have a control hazards. Okay, because you are changing the flow of the execution. It could be anything different totally. So because of the pipeline, the impact is little more, and the impact is much more if the depth of the pipeline is more. I have told you always the depth of the pipeline need not be 5 stages. It could be 9 stages, or even Intel processors have 22 stages. So if the pipelines are too deep, then the performance loss is also high. So a conditional branch is executed. When it is executed, it may or may not change the PC. Again, if it is a conditional branch, the flow control may happen or may not happen. It depends on the flag value. So because of that, you have to make a decision in the ID stage whether the PC has to be loaded with a new value or it can continue with the previous one. So when a conditional branch changes the PC, new address, target address, it's called a taken branch. The branch has been taken. So it is called taken branch. If it falls through, that means what? The sequential execution continues. It is not jumping back or jumping forward. The instruction execution continues. That means it falls through. The execution falls through. After the jump instruction, it is falling through. Then it is not taken branch or untaken branch. Okay. These are all some standard terms used in the architecture world. Based on the status of the conditional flag checked, the decision can be taken. It's always based on that. Whereas unconditional branch is always taken. There is no doubt about it. It has to go to the new location. That's all. Okay. And not only unconditional branch, even a call, a function call, a subroutine, or in ARM we call it as some branch to some function routine where the return address is stored in link register. Those instructions you would have heard. So unconditional branch is jump is one example, or calling a function is also like an unconditional jump, because it will go there for sure, but it will come back later. But anyway, pipeline has to be flushed. The control has to go. So it's equivalent to unconditional branch, except that in terms of unconditional branch, the execution need not have to come back. Whereas in call, it is like unconditional branch because it is going to take a branch for sure. There is no doubt about it, but it will come back. That is a minute difference between a conditional branch, unconditional branch, and a function call or a call routine, which is assembly routine to go into another function. Is there are some minute differences which I have brought out now. So once the decision is taken that it has to branch, the sequential instructions which have been accessed prior to the branch are all sorry, actually I need to change it little bit. Prior to the branch decision. Okay. Okay. Let me rephrase this sentence. Don't get confused. I will rephrase it. What I mean by that, let me tell you. Some instructions are here. Some branch instruction is here. Branch. Okay. I'll call it as branch instruction. Sorry, B is very bad. And then some instructions. Now branch instruction is taking a decision after some time, maybe few cycles, 1 or 2 cycles. Then there are some instructions which have been accessed already. So we need to flush only these instructions, not this. These instructions which are prior to the branch need to be executed. So do not read this statement. This statement is little bit not clearly coming out. What I meant was, after the branch instruction, whatever is here, which have been fetched later on, need to be flushed. And then if the decision is taken, that means it has to go to some other new location, then it will be the pipeline flush will happen. That is called control hazard. Okay. So this is a disturbance to the pipeline and it's called control hazard. Okay. Now let me explain with the example now. Okay. So this is a control hazard with the untaken or taken. Okay. So imagine there is a branch instruction which is instruction I. It is untaken. Suppose it is a conditional instruction and it has decided that there is no need to go to the new location. Then what will be the pipeline stage? It will be I plus 1, I plus 2, I plus 3, I plus 4. So there is no impact to the PC value. PC continues to be the sequential addresses and there are no additional stalls introduced in the pipeline. But what happens to this instruction? It will go through the complete pipeline. Though the decision has been taken here. Okay. If you have seen the latest pipeline structure I showed you, the decision has been taken at this stage that it has decided that there is no need to move to a new location. So it will continue with the instructions which have been fetched, but it has to go through these stages, though it has nothing to do here. Okay. It has nothing to do here, but it cannot just vanish from the pipeline. It has to, if it is entering here, it has to go out here unless there is a flush. Remember, an instruction will have to go through the pipeline completely until there is a flush. It cannot vanish suddenly from the pipeline in the middle of the pipeline until everything is flushed and new instruction is loaded. So this instruction, which is a branch instruction, most likely it is not taken, means it is a conditional branch instruction and it has decided that there is no need to change the flow. it will continue here, but it will not do anything. And then the next instructions which are coming in will continue into the pipeline. It will go into the pipeline. So there are no stalls in this case. Now look at this situation. A taken branch. This is a, it could be either unconditional or conditional, because it is saying that it is a taken branch. So if a decision is taken in this stage, let us all always assume that we have the adder and the flag checking, everything is done in ID stage, that hardware is there. So please remember, this assumption is based on whether we have the flag and the adder, additional adder are there in the ID stage or not. So it's always based on what is in the pipeline. We cannot make a decision that it will be taken here, the decision will be taken here, until we know that the pipeline has an adder here as well as a flag checking circuitry here. So I am assuming, because I introduced you to the latest one, so we assume that it is there. Then the taken branch decision is taken here. But prior to that, already I+1, which is nothing but PC+4, has been accessed. So it is inside the pipeline. Once the decision is taken and the new instruction, targeted instruction, branch to target, that instruction is fetched. This is already in the pipeline. Okay. But we don't want to do anything with this when it moves to EX stage, because we don't want this instruction to be executed and go through this, because it is not supposed to be executed. Let me explain. Suppose you have a branch jump on carry, let me call it as branch jump on carry, and then one instruction is here. This is PC, address PC, and this is PC+4, which has been accessed after the JC has been accessed and it is inside the pipeline. Now, after JC, whatever has been accessed need not be executed because jump is happening. So we need to allow this instruction to die. As I told you, it cannot just like that escape from the instruction. So one stage, one cycle, during this cycle, these instructions are getting executed in different stages, but the module which is above will be doing nothing. Okay, that's what is called idle. I hope you understand what I mean by idle, because let me explain. Suppose it is moving to the new branch instruction which is being accessed here. During that time, this instruction which is there should have moved to EX stage, but nothing, it is not doing anything. Similarly, this instruction which is at PC+4 should not have been fetched, but it is fetched, but should not be executed because it should not change the state of the CPU. So it will also, it is not going through actually. Hardware will take care that there is nothing happening. Okay, during these stages, nothing is happening, and this instruction will come as if it is the first instruction to enter the pipeline. So it will come in and then it will go through. So this is the new branch target address instruction which is getting executed in the pipeline. I hope you are able to understand what is happening here. This is very important. When I give you a picture and then make some statement and ask you to say whether it is true or false, you should be able to relate what is happening. This is all happening in particular cycle. This is all happening in another cycle. So remember, there are stages in the pipeline which are there, physically there. During each cycle, during each time, what is happening in each stage is shown here. So this is IF stage, this is the ID stage, what is happening, which instruction is going through, and this is the PC+4 which was flushed out, and this is the branch instruction itself. So it is all the places where those instructions would have been. Okay, so I hope this is clear now. Now let us understand what can we do some more optimization. Can we do some more optimization? Can we make it little better, in terms of cycle loss? I told you either jump or a unconditional branch or a conditional branch, one cycle is wasted. We are wasting one cycle. One cycle wasted in the sense one instruction should have been executed and we are not doing it. So let me explain what I mean by that. If you see here, we are saying one cycle is wasted. Actually, if you see, it is not even one cycle. Okay, one instruction is lost. That means that one instruction would have gone through different stages. So these modules which should have done exe job, which you should have done memory access job. And as far as this instruction is concerned, it is id and then ex and memory and write back should have happened. Now what happened is, because of one instruction which is coming in, okay, immediately after the branch, okay, you either have a jump on carry or a jump instruction. Okay, now assume that it is branch is taken. This is always taken unconditional branch, and there is one instruction which is fetched, pc plus 4, one instruction has been fetched. Now what is happening? Because of this decision that it is going to be moving to a new address, we are accessing this instruction which is in the slot next to the jump instruction, and we are making it flush, we are making it invalid. So when we do that, this during this cycle, whatever was supposed to have been done in each of those stages, nothing is happening. We are just idling those hardware modules. These hardware modules are doing nothing. They are all doing nothing because we have to forego this instruction. Remember, when in the CPU, we have built hardware and then it is running at a very high fast clock rate. We want to use every bit of the hardware effectively. We don't want to waste. We don't want some stages to be in idle stage. How can we do it? Can we make use of this particular 5 cycles we are just wasting? Okay, in fact, I can say 5 cycles are wasted, but in literature, we always say that there is a delay of 1 cycle because we are getting the another instruction in the next cycle, but it is not going to fill this gap. It is not going to fill this gap. This instruction is coming in late. So what should have been done here is lost. Throughout the pipeline, that is lost. So effectively, if you understand in deep, one instruction should have gone through the pipeline completely, but we have lost the opportunity. Can we do something? What I suggest, if suppose I have an instruction which is above jump on carry or a jump, okay, some instruction which is there, which should be executed, okay, it should be executed, but I don't want to execute it here. I don't want to execute it here. If the condition is this instruction, either it is executed here or little bit delayed, if it is not going to change the flow of the instruction, if it is not going to change the state of the CPU. Okay, I will explain to you with an example soon. Imagine an instruction is there which is independent. Maybe I am loading, saving something, or some instruction, some activity which I am doing it here, some instruction is doing it, and I know for some, let me not talk about Japan carry, okay, or anything, okay, any instruction. I know that this slot is going to be wasted. Okay, if suppose jump is happening, this slot is going to be wasted. I'm going to waste that cycle because that is going to be filled with idle. So can I fill that slot? I call it as a delay slot. Okay, because I am going to delay the execution of instruction. So that slot, which is meant for the instruction, which is point PC plus 4, which is pointing here, is a delay slot. I call it as a delay slot. And instead of filling it with some instruction which is following from JC, I move some instruction. I move means assembler or a compiler takes care of it, and move some instruction which is independent. Whether it is executed before jump or after jump doesn't matter, as long as the instruction is executed. In that case, if I move it here, I don't need to actually idle it. I can go through it completely and all the stages are used. Okay, keep it in mind. This is what as the plan I have. Let me explain it as I go, okay, with an example, then you will understand. That is what we are going to call it as a delayed branch. Okay, now I am jumping the gun. Let me explain it in order now. Delayed branch. Okay, what is that sentence means? It's a solution for a control hazard, because we know that control hazard is going to lose one instruction going through the pipeline completely, because it is going to lose the time. The idea is that a branch instruction does not cause an immediate branch, because it's not jumping immediately, but is delayed by some number of cycles. See, actually branch is not happening immediately, right? We know that one instruction has been already fetched and there is a delay of one cycle, which I mentioned. So branch is really happening with a delay of one cycle. Some cases it may be 2 cycles or maybe 3 cycles based on the pipeline structure or depth of the pipeline. When is the decision taken whether branch is happening or not? Based on that, the delay can be more. Now, we are actually wasting the cycles because of the delay, because the decision is taken after some cycles, after a few instructions have been fetched. So it depends on the pipeline, length of the pipeline, as well as whether we have an adder and a flag checker and all that in ID stage or later stages. It depends on that. Okay. Now, okay, let me explain. If the delay is one cycle, as an unconditional branch, the instruction immediately following the branch would have already been fetched and would be in the pipeline. Okay. So now what is happening? Because some instruction, which is maybe add or subtract or some instruction, which is in the pipeline, okay, which needs to be flushed. So we need to have additional hardware to introduce an idle state in each of the stages. Because of the jump, this instruction coming here, we have to introduce idle stages. So we need some hardware to take care of it. Now, if I put some hardware there, I am using some chip area. Okay. So instead of that, instead of having that hardware which is verifying it and then removing the idle state, what can compiler do is, or an assembler can do, it knows that jump instruction is there, so the next instruction will be anyway going to be flushed. Then it can put a no op. No op is NOP. In Intel processor it's called NOP. So what does it mean? This is an instruction which does nothing. This is an instruction which does nothing, but is an instruction which occupies 32-bit of word length, and it goes through each stage of the pipeline without causing any state change to the processor. That means no register content is changed, no flags are changed, but it quietly goes through the pipeline. Okay. Then the delay slot which I mentioned after the jump instruction, I can put a no op and I can still have the no op instruction going through the pipeline, but without causing any state change to the CPU. Now, what is the advantage we get by introducing a no op? We don't need a hardware to take care of flushing the pipeline, keeping the stages of the pipeline idle. These are all some additional check has to be done, some hardware has to be put. Instead of that, you have a software solution wherein wherever there is a jump, no op will be put next to it. Okay. This is one crude way of avoiding that hardware. So no op is occupying the delay slot. Now, by now you should know what is the delay slot. Delay slot is the instruction just next to the jump instruction. Let me call it as an unconditional jump. Even conditional jumps also delay slot is same. Okay. There is no need to introduce any bubble in the pipeline because existing no op does not cause any change to the CPU state. So no changes to the registers or flags. What I mean by state of the CPU. Remember, you should relate it with the context switch that I spoke on in the OS course. When we want to save the context of the CPU, we say that it's a register values and the flags value in the CPU which is being saved. That is the context of a CPU. So when I say that an instruction going through the pipeline will not cause any change to the state of the CPU, means it doesn't change the content of any registers. It doesn't change the contents of flags. And of course, no memory content should be affected. You should not do some load or store something and then impact the memory also. It's important. Okay. That is implicit. I assume that you guys know it. So this increases. Now, what is the problem with the no op? It is an unwanted instruction which has been pushed into the code area, right? We really don't want a no op to be sitting there, but we don't want a hardware to flush the pipeline. So we thought, okay, let me put a no op instruction forcibly into the instruction sequence. Now what are we doing? We are increasing the size of the code by 32 bits, 4 bytes. Every jump instruction will have a no op next to it. That means effectively we are increasing the size of the code, which is again not a good solution, because remember, even if I have a no op instruction, it has to be stored in the memory. It is part of the code image. It is brought into the main memory. It is also brought into the cache, and it is brought into the pipeline, and then it goes through the pipeline. So you are doing something knowingly that no op is not going to be useful, but still we are getting all through the stages to do nothing, which is a total waste. But we are doing all this because we want to save some space in the chip. We don't want to put a hardware to introduce some delays, idle stages. So why not improve this solution? Why not think something innovative, that instead of putting a no op, as I told you in the beginning, why not I move some instruction which is independent of the flow, whether it is executed before the jump or after the jump does not matter. It does not change the intent of the program. Then I can move it. Now what am I doing? I am moving one of my instruction into that delay slot. If I do it, I am not introducing a new instruction now. So code size is not increasing. The existing instruction which should have been executed prior to the jump is executed later without affecting the correctness of the program. That is very important. You cannot just push any instruction into this slot. You have to choose an instruction which doesn't matter whether it is executed before or after, but it should be executed. But I make sure that it is executed after the jump, so that I don't need to push a no op into the delay slot. So what am I saving? I am saving code size. I am not putting new no ops for every jump instruction. I am not introducing a no op into the code. So code size is not increasing, and I am not bringing that into the chip from the memory and then running through the pipeline, saving a lot of wasting a lot of power is also saved, because I am executing one of the valid instructions only during the delay slot. So this is a very, very important concept which is widely talked about in the architecture world. You have to understand this if you say that you have attended an advanced processor architecture course, because the process course is an advanced course, so you have to have some advanced techniques which are implemented in the processor, and you should know clearly what it means and why it is done in those processes. So we are saying that no op is introduced. Then one second, there is some message, I suppose. Let me check. Okay, is it same as out of order execution? You are right. It is not executing in the out of in order. The instruction which was above jump should have been executed in order. I agree, but it is executed out of order. But in this case, even though it is executed out of order, because instead of executing in the front, it is executed here, correctness is assured. Okay, so there is no need to do a correction afterwards. See, I will come to that immediately on scalar processor. A little bit of deviation from here I will talk about, where out of order execution is happening, and then it is made as in order later on. When the results are put into the registers, they are they are completed in an order. Okay, so here what we do is we don't change the order in terms of submitting the results also. It is submitted, suppose this instruction is some add R1, R2, R3, it will write into the register the way it would have written it to the register here. So we are not going to change the way it is behaving later on after executing it. So let me explain. There is a little bit of difference between what we call it as out of order and in order. That will become clear when I speak about scalar processors. Right now, what you said is correct. It's an out of order execution, because the instruction which should have been executed before the jump is moved after the jump and executed. It is out of order. But we are choosing the instruction very carefully that even if I move it, the correctness of the program is not modified. It doesn't matter whether I do it there or not. As long as I execute that instruction, that need to execute it. It's not that I can just skip it. It has to be executed, but I am not changing the correctness of the program. Okay. So good question. So now no op, we are doing it. What is the advantage of no op? There is no need for a circuitry. That's what I told you. No op, there is no need of circuitry to flush the pipeline. So we are saving some real estate in the chip. But it's a waste. No op is a waste in terms of putting some instruction which is of no use. Okay, so that's why we are now going into another implementation, which I actually explained you already. Okay, now before that, I will show you the example of what I mean by delayed branch. Okay, so this is actually same as what I showed you earlier. I don't see any difference, right? This picture I already shown you. So only thing is I am calling this instruction as a branch delay instruction. Okay, I am calling this as a branch delay instruction, and a major difference is here anyway it is correct. If it is a branch is taken, we would have put an idle stage here. Okay, we would have put an idle stage here if it was not a branch delay instruction. So the major difference now is this is the instruction which is not just behind the jump instruction. This should have been prior to the jump instruction, which has been moved here. Okay, remember, it's a branch delay instruction, means it is an instruction which is executed delayed. Delayed means it should have been executed prior to the branch. It is executed delayed because of the branch, but we are using this delay slot. We are using the delay slot. In that case, we are not going to make it idle. You should not do that because this actual instruction should have been executed. We are doing it. And now if you see, nothing is wasted. Not even one cycle or not even one flow is wasted now. Either branch is taken or not taken. The pipeline is full. You get a pipeline performance of 5 instructions. Every instruction, now every cycle one instruction coming out. You have a 100% efficiency of the pipeline because of one innovative solution by introducing an instruction which should have been executed above into this. Now, nothing comes free of cost in the world. Okay, don't think that I can do it very easily. First of all, compiler, if it is generating an assembly code, or if it is an assembly program somebody has written, assembler has to do this job. Mostly it is done in a compiler level. Compiler has to be intelligent enough to look for such instruction in the sequence. It has to look for it, and it cannot afford to make a mistake. So a compiler has to do a data flow analysis of which registers are used, which are dependent, and is there any instruction above the jump which I can move without any issue into the delay slot. You may wonder, if suppose compiler is not able to find one, it is not able to find, there are no instructions which can be moved, then it will introduce no op. There is no other go, because anyway it is trying to do maximum possible. If it is not, then it will put a no op. Anyway, nothing happens. No op also goes through this stage, but idle is not introduced, but it doesn't harm anything. So it goes through without anybody noticing it. So what is the additional load on the system? Compiler has to be intelligent enough. It should find out the instructions which are independent, which can be moved here. And if it is not found, no op has to be put in. So these are the additional effort has to be taken. So what we have done, as I told you, hardware and software team needs to work hand in hand. The compiler developer needs to work with the hardware guys, and then hardware guy will say that, hey, I am removing the pipeline flush here, that logic which is for the delay instruction. I don't think that pipeline flush will be removed permanently. There are some occasions where it has to be done. Some interrupt happens or something, you have to do a pipeline flush. I'm not saying that pipeline flush will be completely removed, but processing this delay instruction, delay slot and introducing the ideal state is removed, and we need a compiler support for it. So compiler has to do that. Okay. So here we are assuming that only one delay slot, okay, not multiple delay slot, provided additional hardware are available in the pipeline. So that also compiler developer should be aware of. So let me explain one more problem here. Okay, it's very difficult to little bit comprehend and understand. Let me explain now. Imagine there is a compare instruction which you have seen in ARM, which does a subtraction of R1 and R2 without changing the value of R1 or R2. Okay, if you remember compare instruction, it does a subtract. ALU does a R1 minus R2, but it does not change any of these registers. But it affects the flags. It affects the flags. Flags are updated. Now, when the compare instruction is performed, okay, flags are affected, and if it is zero flag is not set, that means they are not equal. R1 and R2 are not equal. That means when it is subtracted, it will not have a zero value. So zero flag will not be set. So result will not be zero. It's a non-zero value. So zero flag will be zero, and branch not equal to instruction will take a jump because it is checking for a zero flag to be zero. I hope you understand it, what I mean by that. Zero flag is not set. So B and E has to move now. Imagine a situation, it is 100% going. Okay. Now, I have introduced a branch delay instruction in my compiler. Our compiler is not intelligent enough, and it has put a branch instruction inside that. A delay slot is having not any normal data processing instruction. It is having a branch instruction. Now, what is the impact? It is like a puzzle. Okay. Just think about it. What we want to do, if this branch is taken, we want some instruction to be executed, okay, in this slot, but we want to continue with the execution here. Remember, our intent was, if a branch is taken, my intent is to go to the target address here and execute some instruction. But I told the compiler guys, hey, put some delay instruction in this slot so that I will execute it without any problem in the pipeline. I don't want to waste the pipeline. Now the compiler by mistake has picked up another branch instruction into the slot. What will happen? It's like a deadlock. Do you understand this? Actually, branch is taken. So I do not want to execute anything below. Okay. I do not want to execute anything below, because I have a slot, delay slot, which I don't want to waste. I have put some instruction from here to this place. Now, by mistake, a compiler guy has put a branch instruction there. Now what is happening? My intent was to go somewhere, but this guy has put another branch instruction, which is going to take me somewhere else. Then my intent of originally going somewhere is lost. Do you understand this? So what is the solution? The solution is the compiler should be intelligent enough not to put any branch instruction in the delay slot. It can put a no op, no issue, but do not make a mistake of having two branch instructions one after the other, wherein this is supported, which is expected. I want the CPU, see, remember, CPU is expecting in a delay slot an instruction which is quietly executed in the pipeline without changing the control flow, because original intent is for me to go to the branch target. this should not cause any change to the flow of the instruction. If I put some instruction which is violating this assumption, it is wrong. So it is not allowed. That means hardware cannot, it is very difficult. It is also possible to say whether I am getting another branch within one branch after the other, then it can raise an exception and cause some issues. Okay, it depends on implementation, but compiler should not put another branch. Now you may wonder if it is a compiler which is taking care, but I am an assembly programmer, I am very intelligent, but I make a mistake like this, what will happen? Then assembler which is assembling this program should either give a warning or give an error saying that their branch followed by another branch is not allowed, because it is going to cause a confusion and it is going to be misbehaving. The code is going to misbehave. It is not going to go there and it is going to go here, and there's a lot of issues. Why is it happening? Please remember, it is not happening just because this instruction is wrong. This instruction was there before, but it was done out of order. What I explained to you, it is done out of order. When you do out of order execution, you have to make sure that the flow is proper. If it was somewhere here, it would have gone somewhere and then done something, right? But you only made it move here. That means you allowed this instruction to be executed, you allowed this instruction to be executed. After that, you are moving now. This is too late. It is like this. No, you want to go to Yangon, but the bus, when you were getting in, instead of going to Yangon, it went to some other city. And then whether it is taking it to Yangon or something happens. Your intent is totally gone. You didn't want to go somewhere else. So this is a unacceptable situation. Okay. I hope this is clear to you. I think this explanation is given here. Please go through it. If you have any doubts, ask me offline, online, or during the next class, or now. There are no chats now, so I can go further. Okay, I will explain this and then stop here for a break. Delay slot with an unrelated instruction. So I told you this is a solution we are talking about. I'm going to explain to you this, how it is performed. Now look at this flow. Just understand this instruction. There is some move instruction which is moving a value from R3 to R2. Okay. If you remember, move does not affect the flags because it is just moving the value from one to the other. It doesn't affect the flag. And what is the next instruction? Compare R1 and R10. Okay. And then jump not equal to somewhere. I want to go somewhere. Otherwise, I want to execute this instruction. Okay. Now, remember, if it was a normal flow, this would have happened before this jump. Either this jump happens or does not happen. This will be done for sure. Agreed or not? Whether the jump, it is a conditional jump, it may happen or it may not happen based on the value of R1 and R2. So it has to go somewhere if it is required to go, otherwise it will execute here. But whether it is going here or here, I want this move R2, R3 should have been executed. I want that to be executed for sure, irrespective of whether decision is this or this. Okay, whether you are going somewhere or continuing with the down. Now, in a normal case, our compiler is not intelligent enough. It would have put a no up here. But I am asking the compiler, don't waste this whole thing. Put, now you know that this instruction has to be executed for sure. But as long as, even if suppose JNE is going there and then it is immediately using the value of R2 or R3, remember this instruction is coming next to this instruction. Okay, remember this, wherever it is going, this instruction is, suppose it is using these values, it is coming next, after the JNE only it is coming. Now if I move this, move R2, R3 into this slot, it is ahead of the pipeline. It is ahead of this instruction. It is there in the pipeline. Later on, this is going to come into the pipeline. So R2 and R3 should have happened, and then only it will be executed. So no issue. If I take a jump, no issue. Okay, if I don't take a jump, I continue further, also no issue, because move is executed. After that, this is executed. Even if I have some instruction which is dependent on R2 and R3 value, there is no harm. Even if I have a dependent instruction which is either it is R2 or R3 here, I don't have any issue because this instruction is executed prior to that. Similarly, this instruction will be executed sitting here before where this jump is picking up the first instruction, because it is going to come next to this pipeline. You have to keep it in pipeline in the mind. Then you will know that moving this instruction does not harm at all. What do we gain? We gain a big deal. Pipeline is completely full. It is executing all valid instruction which are required, and correctness is assured. No cycle is wasted, no stage is wasted. Perfect solution. There is no need to add a no up there. I move here. So I save 32 bits of code size, and I save a lot of cycles. In the sense, a lot of the hardware is not wasted. So this all become because of this is possible provided such instruction exists in the flow. You cannot create some instruction just for it. Okay, don't think that it will be created. Some new instruction will be created. It should have been there, generated by the compiler for some purpose, and it is moved if it is possible and safe to move. Okay, this is very important concept, and it's an innovative concept in the architecture. It's a combination of compiler and the processor doing a job. It is not possible for a processor to do it because it cannot make move come here suddenly. It should have been done during the compilation time. Okay, it is not possible for the processor to rearrange that. I'll talk about it later. Okay, as far as this CPU is concerned, it cannot rearrange the instruction internally. Okay, because it is fetching one after the other. It is in the memory. Okay, it cannot do. Hello. Okay. Is the screen visible? Are you able to see the slides? Okay. Okay. I'm hearing so many yes. Okay. Thank you. So I hope this is clear to you. Presume. So I do, a compiler do, not me do. Compiler is doing this. So filling the delay slot with a no-op instruction is a waste of CPU cycle and instruction memory. Instead, if the compiler is intelligent enough to fill in the delay slot with an instruction which is part of the program, that is ahead of the jump instruction, which is ahead. Okay, ahead means I call this one into the slot, then the solution becomes efficient. Okay, I hope it is clear. In the example above, the original code is rearranged to move down the move instruction below the jump instruction by the compiler, which always gets executed by not affecting the correctness of the program. So it is always executed. Don't think that even if jump is happening, this instruction is executed, but not this. Remember it. Let me, if any of you have any doubts, remember it. Because of the way pipeline is behaving, the delay slot instruction is executed after, even when the decision is to take the jump. So the jump is going to be taken. It is going to execute this instruction. Okay, let me call it as a X, Y. Okay, these are the instructions which are executed when jump happens. Then if I ask you, list the instructions which are, list the number of the instructions which are executed one after the other if jump is taken, if JNE is taken, then you should say compare is executed and move is executed JNE is executed and X and executed, Y is instructed. You can even order it differently, but it will look odd, but you can still order it in a different way. Okay, let me explain what I mean by ordering it differently. Suppose if I ask you what are the instructions which are getting executed if the jump is taken, and the first instruction is X and next is Y in the target address, then you can say compare is executed, then JNE is executed. Actually, in the pipeline, it is true. JNE is only executed first. Then move is executed, X is executed, Y is executed. You can conveniently assume this move is moved just before X also. It is equivalent to that as far as if you see the pipeline, it is equivalent to that. But correctness is assured. So that is how it is taken. Now, if I ask you a question, give me a list of instructions which are executed assuming jump is not taken. Okay, assuming jump is not taken, then you have to say compare is executed, JN is executed, the decision is not taken, then move is executed, then sub is executed. So that is the flow, the sequence of instruction executed when JNE is not taken, blue is not taken, okay, not taken, and red brown is taken. So the sequence of instruction is, if it is taken, it is this executed with the condition that it is taken, and move is executed and X and Y is executed. So if you understand what I just now told you, you understand delay branch, you understand how compiler is performing an optimization in terms of getting the best out of pipeline. Compiler is helping us to get the best out of the pipeline. Okay, so this does not waste the delay slot. Okay, so I am going to have a demo after the break of the simulation tool. So enjoy, come back after 10 minutes. Recording. 1 second, hold on. If move has R1 and R10 values as a destination, it cannot be done. Move has to be executed first. Okay, let me, 1 second guys. I have to go back. So the question was, suppose this move, okay, this move was having R1 and R10 values as destination. Okay, you cannot have two. Okay, what she means is, suppose if I understand her question, this is not R2 if it was R1, suppose, or if it was R10. Okay, suppose. Now what is happening? We want the R3 value to be either moved into R1 or maybe R10 here. Okay, move can only move into one register. So if this move instruction was like this, can it be moved here? Can it be moved here? I am sure you guys will know it's not possible, because compare is performing a comparison with this value, okay, two register values. So if it is moved here, it is not going to have a new value which is was in R3, which is moved into those registers. So it is not an independent instruction. So this is a good example of not to pick some instruction which has an influence on this. Okay, this should not be data dependent. The instruction which you are picking up should not be data dependent on the instruction which are above JNE. If it is so, then you should not pick it up. The compiler will not do the job of picking this instruction if it was having R1 or R10. Okay, so I hope you understand this. It cannot be done. You have to pick some instruction which can be moved without affecting the correctness. But here we are affecting the correctness. If it was R1 or R10, if these values are R1 or R10, this one of this, okay, the destination is R1 or R10, then compare will is dependent on this. Compare is dependent on that instruction, so it will not be moved. Okay, some other instruction will be picked. If nothing is there, no op will continue to be there. Okay, okay, I hope it is clear now. So let me stop now. What is the time? exactly 109. Okay, 320, guys. 320 will meet back. Come back. I'm going to give a demo of the tool. Bye bye. Hi. Should we start? Hello.
Yes.
Okay. So let us now look at some tool which I wanted to introduce much ahead. I told you guys to go through it. I don't know how many of you try to use it. Now, all of you have studied about pipeline and almost all instructions when they go through the pipeline, what happens to them. So this is the right time to introduce you to the tool so that you can play around with that and understand it, what happens to different instructions. Okay. Now, let me explain before going into the tool, another concept which you are supposed to know. See, this is same pipeline which I showed you, except that the EX stage, the execute stage of the pipeline is replaced with multiple units. Okay. Instead of having single ALU, I am showing it as a different hardware, but it is in the middle of the pipeline. Okay. It is in place of EX stage, you have different hardware units. Now from the names you can make out, this is just an integer unit which can perform integer addition, subtraction, logical operations, and or those operations, all that can be performed by this hardware. And if you see the arrow marks, you should by now be able to understand what is this particular line talks about. And some are shown straight like this. It means this unit, integer unit, takes only one cycle, like ID and mem in an ideal situation. Okay. In case of memory and in instruction fetch, ideal situation is one cycle. If there is a cache miss, it can be more. But in the hardware, once the data input is available and output has to be produced, there is a fixed delay in this. Okay. Maybe in floating point, based on the performance, based on the operation being performed and the value of the operand, there may be some difference in the number of cycles in floating point arithmetic. Whereas mostly in integer arithmetic, in addition especially, it is always one cycle, whether you have you are adding 1 and 2 or 1000 and 2000, it is going to take only one cycle because it's a simple combinational circuit which is taking all the 32-bit value or 64-bit value and producing the result. So it is built into the hardware that it will do it in single cycle. Whereas other floating point operations as well as integer multiply and division, here it is saying that fp slash integer multiply, this is fp add, and this is fp slash integer divider. So fp means floating point, real numbers. So they are combining these two, floating point multiplication and integer multiplication. Here single unit is taking care of it and it is doing this. Now I am suddenly bringing in a floating point. So let me explain a little bit. When you have an CPU, it is not that the CPU is performing only integer operations. It is not possible to do all scientific computations, simulations, and graphics. Graphics is mostly done in integer, but some of the things, proper image processing and speech processing, there are so many applications, scientific applications, wherein you need floating point numbers because you need to represent the numbers in a minute details. with a resolution of even less than 0 some values. And it is I explained about floating point much way back in computer organization course. So a floating point number could be a 32-bit value or a double, which is 64-bit value. So when a real numbers are to be operated upon, then what we need to have floating point numbers. So in C, we declare as float or double, or we may declare as an integer or short or long, so many things. So if you are declaring a variable as integers, it will be in the integer registers, which are whatever we have seen so far. They're all integer values can be stored there. Either address can be stored or integer values of your programs can be stored in those registers. Now, if you have a floating point number, if you have a floating point values, floating point variables in your program, what happens to those variables? Suppose if you have declared a double, it's a representation of the double is not same as an integer 32-bit value or 64-bit value. It is totally different. The way it is represented or the way it is understood. It can be bit streams. Okay, it's a 64-bit. You have a 64 binary values, but how it is interpreted by the hardware depends on whether it is looking at a integer value or a double value or a floating point value. So normally what happens is a separate set of registers are managed. Floating point registers are different. Why is it so? Don't think that floating point register stores something totally different. It's also storing either 32-bit binary values or a 64-bit binary value based on whether it's a float or double. But those bits represent something different. It is not same as signed to complement value, what you see in integers. But you need a placeholder, a register to hold those values. You can use the same registers that you use for integer. But the problem is you cannot interpret those values like what you do for integer. It has to be separate. Then mixing these two representations and then performing those operations in the hardware is very complex. You have to know every time whether you are reading an integer value from R1 or is it a floating point value. So there is a additional hardware circuitry needed to know whether the 32-bit value stored in a register is an integer number or is it a floating point number. So what is done in hardware is separate registers are maintained and separate set of instructions operate on them. So integer operations like add, mul, divide, if it is an idiv or iadd, we call it as idiv because if the processor supports both floating point operation as well as integer operation, you should differentiate whether you are performing a addition on integer or addition on floating point number. So fadd is for floating point addition, iadd for integer addition. So instructions are modified to represent whether it is an integer addition or a floating point addition. And not only this is sufficient, we are going to have a separate set of registers. So register set is going to be one for integer, one for floating point. So register set, when I say register set, there are set n number of set registers are there. So you may have n number of floating point registers and n number of integer registers. Now integer instructions operate on integer registers and floating point operations, floating point instructions assume to have the values operands coming from floating point registers. So the units are different, the instruction executors are different, and register sets are different, and the number representation is different. So floating point is IEEE 754 format. So in that format, it is represented in the bits inside the register, and the hardware which is performing a floating point addition understands that particular format and performs the addition. So remember, there are two sets of register set, and one for integer, one for floating point. Maybe I'll call it as here, and they have different representations. This is integer, okay, and they will also be operated upon by different set of instructions. Integer instructions operate on this, floating point instruction operate on it. When I mean operate means it will read them, perform some arithmetic, and then put it back. All that happens. Now hardware units performing those jobs are also different. In this case, maybe it is combined integer and multiply. In that case, integer operation means it may read from here, floating point will read from this set of register. So based on the instruction which is coming in, it will find out in this stage whether it is an integer arithmetic or a floating point arithmetic, and whether it is an addition, subtraction, or multiplication. Now, based on the type of instruction, the operands are fetched because it is there in the instruction itself, and then based on the operation to be performed, the hardware is also chosen. So that particular instruction will be fed along with the operand. You have the same pipeline registers are there. Don't think that it is all gone. The pipeline registers are sitting in between, but now they carry different information. They carry both integer information as well as floating point information. So the hardware is much, much more complex than what you have seen so far. So you have to comprehend the complexity of the hardware. I'm not going to talk about I'm not going to show you the hardware structure circuitry because it's impossible for you to understand it in a 1 hour of time. So what happens now? When you have to perform a floating point multiplication, it cannot be done in single cycle. It has to be done in multi-cycle. That's why you see an arrow looping back. That means it is going to spend maybe 10 cycles or 15 cycles to perform the multiplication by the time the result is available. Now, another question. Is it going to perform out of order? If so, what will happen to the instructions which are coming in? The fact that there is only one pipeline like this is shown, only one stage, one hardware unit is shown. Okay, that means what? There is only one instruction can be in this stage, one instruction here, and one instruction here, in one instruction here. That means there is one of the module will have one of the instruction here based on what is coming in. So imagine if you are getting a integer multiplication here, it will move into this stage. Okay, this will be unused. Now next instruction happens to be a integer divider. Now this guy moves here. Now integer divider comes here. Then this will be used, this will be unused. So based on the type of the instruction, one of the modules will be picked up. It will perform the job and give the result. So the flow of instruction is a single flow only. Only thing is it may take like this sometime. Some instruction may go through this, some may go through this. So if I ask a question, how many instructions can be in this stage and how many blocks will be busy during this stage? If I ask you, the answer is one for both. One instruction will be in this stage, and how many blocks will be busy? Only one of them. Based on what? Based on what instruction is being executed currently. If it is performing a integer add, this unit will be busy performing the add during the cycle. They will be waiting. Now see difference, one more difference you have to notice now. Imagine this is only taking one cycle. Okay, this is taking only one cycle, whereas integer multiply, I say that it takes 5 cycle, and floating point adding takes maybe 10 cycle, and divider takes 15 cycles. Suppose if I say that hardware is taking different cycles at different point in time, how will you know how much time it will take for some set of instructions to go through? It depends on what type of instruction is coming in. If there is a divider, then it is going to take 15 cycles. If it is going to take 15 cycles, the rest of the instructions have to wait. This should have been completed in 2 cycles. This will be done. Now this guy is occupying 15 cycles. That means the pipeline cannot proceed. Don't think when this is busy, I may go through this, or I may send some instruction like this. It is not possible in this structure. We are not showing it like that. There are some other instruction superscalar where we have multiple pipelines. Then it is possible. With a single pipeline, they have to follow the sequence. So if one instruction is occupying the EX stage for more cycles, rest of the instructions here need to wait. There is no option. Okay. So with this, I am going to now explain you the simulator. So based on the type of instruction entering, EX stage will take different cycles spent. They will spend different cycles. While an instruction is spending more cycles in EX stage, instruction following it will be stalled until the instruction exits the EX stage. So they need to exit this before the next instruction come in. So let me now show you the tool. I will have to share that. Okay, this link I already shared it with you. Just want to know whether you are able to see the website web link. Can one of you confirm? Can you see the computer architecture educational tools? Hello. Okay. Okay. So there are. This is actually an online tool. Mostly they would have done this tool in Java. It's developed by university, and I want you guys to go through this, understand it yourself, because most of the things have been TLB and cache, all that has been covered, and virtual memory has been covered. But you can try yourself, understand it. I'm not going to spend time. I'm going to spend some time on this part of the tool, okay, which is processor architecture specific, what we are covering. Now let us go into pipelining. Okay. Now you have two options. Either assume that the pipeline has a data forwarding logic built in, or it is not there. Okay. So you can choose based on whether you want to see how the instructions go through the pipeline and what they get into by enabling the data forwarding optionally. So to start with, let us do a simple simulation. Now, let me show you what all instructions are there. This is the MIPS pipeline only, but with the different hardware module that I explained to you, divider, subtractor, and different cycles you can configure it. So there are floating point operation as well as integer operations are there. Okay. Now let us start with the simple integer operations. So let me say integer add r1 comma r1 comma r1. I insert the instruction. When I insert it, I have inserted it twice now. What happens is it shows you the CPU cycles, and these are all 1, 2, 3, 4, 5 shows which stage the instruction is on each cycle. Okay. Now I am assuming data forwarding is not there. Okay. Integer add r1 comma r1 comma r1 is there twice. It is being executed. Now I want to know what happens when this instruction is picked up. Okay. So let us go step by step. I can execute it stage by stage, and it will show you whether it is IF stage, ID stage, and all that. So first is IF. The first instruction is fetched. Next step, next cycle, this moves into ID stage, and the next instruction is fetched. Step. Now this is being accessed, means processed. R1 comma R1 comma R1 is processed, and ID is done. Step. Now you see what is happening. This instruction needs the operand which is R1, which happens to be the destination register for the previous instruction. That means it is not yet available in the register. Now, if it is not available in the register, there is a possibility that I can get it through data forwarding, but I am not using the forwarding. Forwarding logic is not there in this current pipeline. So what is the other option? I have to stall it. I have to stall it. So stall is introduced now. This instruction is stalled. Now step. When the write back happens, okay, if ID was there before, it would have read it now, but ID is already completed. So what happens is the value is still not there. Write back stage also, it is in stall stage, okay, because forwarding is also not there, and it has to be written and read again, okay. It will be the value has to be read unless it is written, okay. So write back has to be there, and once that write back is done, it starts with the execute stage. So what happens is actually there is some hardware logic which will bring what should have been read here in the ID stage. The operand is brought in through the to the pipeline register, so that EX stage continues. So EX stage continues after the result has been written into, okay. So this is without the pipe forwarding. Now same set of instruction, I can see what will happen if I enable data forwarding. There are two stalls now. Will it become one stall or no stall? So let us see now. I enable data forwarding. I execute all. I can execute the instructions together so that I know what is happening. Now it is avoided. No stall is there. Can you now tell me where is the result R1 available, which pipeline register, and how is it coming to the next instruction? How is it fed to the next instruction? From this, you should be able to understand the result is available by the end of third cycle, correct? It is available in the register, pipeline register, which is nothing but EX/mem. It is in that register. And you know that from both EX/mem and mem write back, there are forwarding paths available to the input of ALU. In this case, both operands are read from R1. So it is similar to what I gave you in the exam yesterday. I gave both the operands which is dependent on one of the destination register. If you remember the question 2, it had two operands which are dependent on this. So as I told you, the forwarding paths are 4. 2 from this EXMEM and 2 from MEM write back to both the inputs of ALU. So when both operands depend on this, both operands will be taken from the pipeline. So in this case, what is happening is the result is available by end of third cycle, and it is taking that into the input of ALU. From this register, both the results are same result is fed into both the input, and this continues. So we have no stalls with this forwarding enabled. So this you can visually see by executing this. Now let me do one thing. This R1 is written into destination register again. Now suppose if I introduce a store instruction, I want to store this value. So what I do, integer store, I select, I say that I want to store the value of R1, and let me choose something else. So what I am doing, I am adding the content of R4 with the offset, and in that address I want to write the value of R1. I have enabled forwarding now. So let me insert it now. Okay, see, let me come back again. This R1, this instruction is executed by 5 it will be writing back, but with forwarding it is value is fed to the next stage, next instruction ahead. So no stall is introduced, and we saw that this instruction was going through and this was also going through without any stall. Now I have a store instruction which is interested in taking the R1 value. Now, do you think will there be any stall in this case? So I will launch the same poll. Okay. Think again. I am not going to execute it now. Please don't go to your link and then try to execute it. You can do that. If you have the link available, if you used it, you can just do that. But without doing it, I want you to tell me whether will there be any stall when all these 3 instructions get executed. So let me open it. So you are saying that, I don't know. My question is, will there be a stall? If you say true, that means you are saying there will be a stall. If you say false, you are saying that there is no stall. Okay. So while you are answering, while you are thinking, I don't want to disturb. So let me keep quiet. So both true and false are neck to neck. True options are more nowadays. Now, as on just 34 people have taken. Oh, okay. Let us now, while you are answering, I should do, or I could stop it. Okay, you do it. Only 34 answered. Others are not even in front of the relaxing, all of you. Okay, guys, let me end the poll. While you are answering, you will not be able to concentrate. So let us see what happens here. I hope you are able to see the screen. So I will do a step by step. So we know that these 2 instructions, first 2 instructions, do not have any stall. Okay. If at all any stall has to happen, it is due to the store. Now you have to imagine, oh, sorry, there is a partial result available here. If you have noticed it, you might have given the right answer. I don't know how many of you saw that and given the answer. So there is no surprise. It says no hazards found. That means there is no data hazard as far as these set of instructions are concerned with the data forwarding enabled. So it is already, news is out. There is a answer is already out. So let me execute all of them together. Now look at the situation. Where do we expect a stall? We expect a stall where here we want to write the value. We want to store the value which is in R1 into memory. So it is enough if I have the value of R1 just before the memory cycle, because address I can find out, this offset R4 plus offset I can do it during the EX stage, that is independent. It's not dependent on anything, but I want R1 value during the data writing. It is writing into the memory, that time I want the data. Where do I need it? Which pipeline register I want it? I want it in this. Now, your value, where is it available now? Is it written into R1? Actually, it is written into the first half of this cycle during this time. But you cannot wait till that time because memory has to have the value ready. So it will be taken from one of the forwarding path, which we didn't talk about this memory store in our pipeline. Always we spoke about data hazard with respect to arithmetic operations. So we showed that there is going to be a link forwarding registers to the input of ALU. Here we are not dependent on R4, which is not there in any of those registers. So R4 doesn't depend on any of the previous instruction. So ALU does not need a forwarding path, but this instruction needs it. That also it needs it during the memory stage. So it will either be coming to the data path of memory from the forwarding register, or the hardware could have been structured such that as soon as R1 is written, it could be fed. So it depends on the implementation, but still it is way ahead. No, the value of R1 is already available by the time this instruction is executed. By the time this second instruction is completed, end of 4, the result is available. R1 is available in the pipeline register. Okay, one of the pipeline registers, it is available. And what when we need it, actually we need it during the 6th cycle, so it should be fed. So there is no delay involved in the pipeline. Now if I have data forwarding not there and execute all, what happens? See this, the whole thing is getting delayed. This is also getting delayed because it wants it from the EX stage. It wants, when the operands are read, it wants it. It is not wanting it during the memory stage. It wants the operand to be ready at the in front of EX. So it is introducing 2 more delay. So it needs some more time for you to understand it. See, one thing I will tell you, this whole thing is shown based on some implementation in the mind. And this simulation tool does not really execute the value. It doesn't actually emulate instructions. It doesn't put some values into R1 and execute it. It doesn't do any of this. It just shows you the pipeline structure based on the hardware is in the pipeline. So from the results, you have to understand what is the pipeline, whether the pipeline has an additional adder or not, whether the pipeline has a flag check in ID stage or EX stage. So it depends on so many things. And forwarding logic, whether it is connecting only the ALU or is it connecting to the memory. There are so many things to be understood about the hardware, and there is a help also available. I encourage you to read it, but it gives you some idea about how different instructions behave. And one thing I will tell you, I will warn you, if at all some questions I ask, I may be asking a question basically specifically mentioning that adder is in ID stage or it is in EX stage. So unless you understand the hardware and then execute your instruction through that hardware, you cannot guess the value, and you cannot put it in this simulation and then try to guess the value. Sometimes it may be right, sometimes it may be wrong. So what I suggest is try to play around with this, include some FB add, FP divide, if no these instructions also. You are free to choose different cycles here and then add the instruction. Suppose FP add, you have said that it is 4 cycles, and I will add the FP add now, insert the instruction and execute now. Okay, let me delete some. Okay, I cannot delete the instruction. Let me FP add. Let me show you how many cycles it takes. It takes 4 cycles because we said FP add takes 4 cycles here. So execution unit, it is spending, because it is spending 4 cycles here, everything else is delayed. Now suppose if I add after this one integer add, if I instruction, if I include it and then execute all, then you can go back and see. Now this guy doesn't assume like what I told you. Okay, it doesn't hold this instruction long enough till this is completed. It is going ahead with this. So whatever I showed you the picture is not what is emulated here. Okay, if it was like that, it should have actually delayed this whole thing for that long. So that's what I'm saying. What I explain you in the hardware, it depends on what is expected of the hardware. In this case, what is happening is it is behaving like a scalar processor, wherein this is like a separate pipeline and it is completing it and then it is doing this one. So it doesn't wait for this operation to be completed. Okay, little different from what I explained to you. It can happen because this simulator is assuming that it doesn't wait for the execution of floating point to be completed for the integer. So because it is waste of energy in holding it, so you can decide it that way also. Then it has to take care of so many things. Okay, I'll tell you, suppose let me introduce one more fp add uh, in this and then execute all. Now what happens if you, let us see now, 1 second, let me show you. Now you see here, this is using the same what is being used by the previous instruction, so it cannot use it until that becomes free. So it is holding it, it is stalling this instruction. So it is, its behavior will be different based on how they are imagining the hardware to be, and then it is implemented based on that. So I want you to read the help which is provided here, which is there. Read up this particular thing and then understand it, then it may make sense for you. Okay, this simulation is based on what they are assuming here. Okay, so it's a good thing to start playing around with this tool to understand it. Here it is called structural hazard. You can see it is showing you all the hazards which are experienced by the instruction. It's a structural hazard because add unit is the same in both instruction. You cannot use it when another instruction is using it. So it's a structural hazard because same function execution unit is being used by both the instruction. Okay, so it's an interesting thing to play around and understand it yourself. I'm not going to spend time on running it and trying to explain you. This is something which you can do offline. And I am thinking I will not ask any questions based on this simulation as such, because you can always run it and see the value. Maybe I can ask you, run these instructions and then explain what is happening. That is maybe not given here. You may have to get it from the way it is executing. So that may be one good way of making you understand how this simulation is functioning. Okay, so I am going to stop here today, which you are all waiting for.